After watching this video lecture, students are going to be able to compare and contrast heat and temperature, as well as manipulate the specific heat equation to solve for specific variables. So let's go ahead and compare and contrast heat and temperature. So first of all, heat is a form of energy. Temperature is not. Temperature is actually a measure of the average kinetic energy of the particles in a specific sample. And as we know from kinetic molecular theory, our kinetic energy is going to be directly proportional to our temperature. So our higher our temperature, the more quickly our particles are moving. And so when we have our sample of water and we stick a thermometer in that sample, the particles are going to be bumping into that thermometer. The faster they're moving, the more energy they transfer, and subsequently the higher the temperature reading you're going to have on your thermometer. Okay, now temperature is going to be independent or not depend on the mass or identity of a substance. And we, can think through this. The temperature of, say, a bathtub full of water, I could have a bathtub completely filled with water that has the exact same temperature as a cup of tea. Okay, so your temperature is going to be independent of the identity or mass of the substance. So now that we're comfortable with temperature, heat is basically that form of energy that's going to flow between objects at different temperature. And we totally intuitively understand this because ice cubes, you put them in your hand, they're going to melt. If you stand in front of a campfire, it's going to warm you up. Now, if we think about this, which campfire would warm you up faster? A small one or a big one? If we think for a second, obviously the bigger campfire is going to do a better job of getting us warm after a cold night. And so we intuitively understand that objects are going to transfer heat energy from the higher temperature object to the lower temperature object. And of course we understand that the quantity of the fuel source is going to establish the amount of energy that can be given off. Okay, so heat is going to depend on both the mass and the identity of your substance. And we measure heat in a specific unit called the joule. And basically all your calculations are going to have either joules or kilojoules when it comes to calculating your heat value. Okay, so another thing that we need to talk about now is specific heat capacity. So specific heat capacity is represented by the letter C, and it's the amount of heat needed to increase the temperature of 1 gram of any substance by 1 Kelvin. Or it can also be by 1 degree C. Either way, it doesn't matter. But basically, all matter is going to have its own specific ability or capacity to absorb heat. And the heat capacity of your substance is going to dictate its behaviors relative to, absorbing and releasing heat. Okay, and so if we go ahead and we look at a few examples, we have 3 different examples here. We have aluminum, wood, and steel. You can see that aluminum has, or the ability to absorb 0.9 joules of heat energy in a gram, and that would only cause that aluminum piece, that 1 gram of aluminum, to increase by 1 Kelvin. Okay, and then with wood, obviously the number of joules that it can absorb before that temperature change occurs in that 1 gram sample is a little higher. And if we look at steel, obviously it's lower than both of the previous examples. Okay, so now if I were to make a bike out of each of these 3 substances, aluminum, wood, and steel, which bike is going to be the hottest after it's been sitting in the sun all day? Okay, and if you look at this, the steel has the lowest specific heat capacity. So what's going to happen is it takes less energy to increase the temperature. Okay, so the steel is going to end up being the bike that's probably hottest to the touch at the end of the day, while wood is going to be the coolest. So this is specific heat capacity, and this will be utilized when we're calculating our heat values for specific samples. So our heat equation, Q equals M times C times delta T. This is an equation we're going to use. It allows us to relate heat to the mass, specific heat capacity, and change in temperature associated with the sample. Okay, so each of these variables obviously could be solved for given the other 3, but we're first going to focus on Q, which represents heat. Okay, so Q is the amount of heat. The units here are going to be joules. Your specific heat is going to be joules per gram degree Celsius or joules per gram Kelvin. This is where we commonly have people make mistakes, so make sure that you are not confusing these two, okay? Make sure you straighten these out in your head. This is heat, okay, and this is specific heat capacity, okay? And our change in temperature, when we calculate our change in temperature, we're going to always take our temperature final and subtract our temperature initial, okay? And that will give us our change in temperature for our substance. Okay, so let's go ahead and let's apply some practice with our heat equation. So how much heat is required to change the temperature of 731 grams of water from 28 Kelvin to 347 Kelvin? Okay, so they've provided us some variables and they've asked us to solve specifically for heat. So just like we've done in the past, we're going to write out our variables. Okay, we know that M is provided, so we got 731 grams. We have C because they gave it to us, guys, but you need to make sure that you memorize the specific heat capacity of water because I won't be giving it to you on quizzes or tests. And we will need to calculate delta T. Now, delta T, remember, is final minus initial. So if I go from my house to your house is the final resting place of my trip. Okay, so in this case, it says we're going from this temperature to this temperature. So this is my temperature final, this is my temperature initial. Okay, and so I'm going to calculate that. So 347 minus 281, I'll show that work. Okay, and that's going to give me 66 Kelvin. Okay, and then what I'm going to do is I'm going to go ahead, I'm going to write out my equation. Okay, and in this case, I don't need to manipulate it because it's already in the correct form. So then I'm going to subsequently plug in my variables. So 731 grams times 4.184 joules per gram Kelvin. Remember, that could also be per degree Celsius because it's calculated with delta T. The difference between Celsius and Kelvin or Kelvin and Kelvin is going to be the same. Okay, and then we plug in our temperature. Okay, we go ahead and put this into our calculator, and this is going to give us the following answer, okay, in joules, right, because Kelvin and Kelvin cancels, grams and grams cancel, joules is left over, okay, and if we look at our sig figs, we got 3 here, we got 2 here, okay, so 2, 0, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, joules is going to be the quantity of heat required to increase the 731 grams of water by basically 66 degrees. So this is the approach. These are the steps. Make sure you're showing your variables, you're showing your work, you're showing your equation manipulation, you're plugging in, and you're accounting for sig figs in your final answer. Okay, let's go ahead and let's look at another practice problem. We've been told that 4 gram sample of glass was heated from 274 degrees C to 314 and that it absorbed 32 joules of energy as heat. What is the specific heat capacity of this type of glass? Okay, so once again, we know we're going to be using our MC delta T. Okay, Q, they've provided that for us. Okay, they told us that it absorbed 32 joules of energy as heat. Okay, so 32 joules, right? Our M, they gave us our 4 grams. Specific heat capacity is what they've asked us to solve for. And the delta T is, once again, our final minus our initial. Okay, and we're going to go ahead and do the math. That gives us the following. Okay, and then we need to take our equation. We have our Q equals M times C times delta T. We're going to solve for our C. So C is going to be equal to Q over M times delta T. Okay, so I've done my manipulation here. I'm then going to plug in my variables. I have 32 joules divided by my 4.0 grams times my 40 degrees C. Plug this into our calculator. And that's going to give us a specific heat capacity of 0.20 joules per gram degrees Celsius for our glass. Once again, writing out our variables, showing our work, manipulating our equation, plugging in our quantities, so both number and units, and giving our answer with the correct sig figs as well as correct units. Okay, and so for our final practice here, we've been told that we have a welded layer of copper on the bottom of a skillet. The skillet weighs 125 grams. They have told us that they have the specific heat capacity of 0.387 joules per gram Kelvin. They've told us that we've gone from 25 degrees C to 300, so 300 minus 25 degrees C, so it's going to give us 275 degrees C. Okay, and they want us to calculate heat required to make this specific change. So once again, written out our variables. Okay, this is just a simple Q equals M times C times delta T. Okay, we're going to go ahead and we're going to plug in our values. So Q is equal to 125 grams times 0.387 joules per gram Kelvin times 275 degrees C. Okay, now listen guys, remember I told you this could either be in Kelvin or degrees C. The reason why is because, again, if I converted this to Kelvin and this to Kelvin and then subtracted the two, I would get the same difference in terms of my delta T. Okay, so it doesn't really matter. I can rewrite that as degrees C, or I can just leave it as it is. It doesn't matter to me. So we're going to go ahead, we're going to plug this in our calculator, and that's going to give us the following. Okay, Celsius, Celsius. Okay, grams, grams canceled. Joules is what's left. Got 3 sig fig, so joules, okay, is our answer. So this is the amount of heat that we would need to add to the copper layer in order to get it to change by this amount. Okay, now, if we were to go ahead and do this same exact problem up here, but instead of increasing the temperature from 25 to 300, let's say that we were already at 300 and we wanted to find out the amount of heat change associated with decreasing the temperature down to 25. So in that case, all of the work here would be exactly the same, right? So we'd still have 125 grams. We'd still have the same specific heat capacity because the substance's identity hasn't changed, okay? But in terms of our delta T here, our final temperature is going to be the 25. So 25 minus 300, that's going to give us negative 275 degrees C. So when we go and we plug all these values into our equation, right, our Q equals M times C times delta T, okay, we're going to have 125 grams, we're going to have our 0.387 joules per gram Kelvin, okay, and then we're going to have our negative 275 degrees C, okay. And when we calculate this, we're going to get the exact same answer as we see up here. The only difference is that the negative sign is what we're going to have, okay. And so the amount of heat exchanged is exactly the same as what we saw up here. The difference is this negative value. And this negative value doesn't mean that there's negative heat. What it means is that the copper, or what we would call the system, is giving away heat, or it's losing heat. So this signage is telling you directionality of the heat flow. It is not telling you that there is less heat associated with this change versus this change. Okay, so hopefully that makes sense and you feel confident with your calculations.